那第一位演讲嘉宾是拉斐尔·萨克斯，他是以色列理工学院土木环境工程学院教授兼虚拟建造实验室主任，阿什特罗姆工程公司土木工程主席，以色列国家建筑研究院院长。他的报告题目是从 BIM 到数字孪生建造。好，大家欢迎。
So I want to say thank you very much. I hope you have found this interesting, and I am available to answer questions. Thank you very much. I work with the Seskin Virtual Construction Lab at the Technion in Haifa, Israel. We work on lean construction. We work a great deal on building information modeling, where we study, experiment with and develop BIM technology, process, and people. We also work in the synergies of lean construction and building information modeling, and that's been a long period of research which has now resulted in commercial products for use in construction management. So what am I going to talk about? I'd like to just lay out quickly as an introduction what is building information modeling in the way that we see it. And when I say we, I mean the authors of the BIM Handbook. And then we'll dive into the question, what is digital twin construction? And finally, we'll ask the question, how can we advance from the BIM that we know today to a digital twin construction industry?
当前的建造行业有2个概念，精益建造和 BIM。精益建造关注于复杂建设项目的工作流程和人员团队 ，BIM 则对 BIM 技术、流程和人员重点关注。精益建造和 BIM 的协同，就需要通过可支持 BIM 的系统来支持施工现场和生产计划。本次报告将通过3个部分介绍从 BIM 到数字孪生建造的发展。
Well, I had a wonderful mentor, Professor Chuck Eastman at Georgia Tech in Atlanta in the US, and he described in 1975, almost 50 years ago, coming up soon, a building description system, and he said that designing would consist of interactively defining elements. That elements would automatically be consistent. One type of quantitative analysis could be compared directly to this description. And he also said that the BDS will act as design coordinator and analyzer, providing a single integrated database for visual and quantitative analysis. Later, one could conceive of a BDS supporting automated building code checking. Well, the BIM systems we know today have fulfilled all of his predictions from 50 years ago, perhaps except for the last one, which is still the subject of ongoing research. And so, if we think about what building information modeling is, then we can say this. With BIM technology, we can create one or more accurate virtual models of building digitally. The models support all the phases of design, allowing better analysis and control than manual processes, especially functional simulations. And in that sense, they function as digital prototypes whose behavior and performance can be thoroughly tested, measured, and evaluated. The digital models contain precise geometry and data needed to support construction, fabrication, procurement, through which the building is built and operated and maintained. So let's just quickly have a look at those different aspects. As I said, we can have one or more accurate virtual models of the building constructed digitally. In this case, an office building in Singapore called Mapletree Business City. And you see quite clearly that there are distinct architectural, structural, and MEP models brought together in a federated model. Or in this example of a hospital called the St. Joseph's Hospital in Denver, Colorado in the US, where it's an entirely detailed model and was used from design through fabrication and is now being used in operation. And then we talked about digital prototypes. And this is a building in Tel Aviv in Israel called the Porter Building. We see here the digital prototype used in this case for lighting analysis and for visual consideration. But interestingly then, of course, because it's a prototype, we can compare it to the actual real building, which we see here. And we see that almost all of the decisions made in the prototype building in BIM did come to fruition in the real building, as you see here. We can talk about precise geometry and all the data needed to support fabrication. This is an image of the Louis Vuitton Foundation building in Paris, France. And this was a highly complex building to fabricate. Every joint in the steelwork was different. It's reminiscent in that way of the Bird's Nest Stadium in Beijing. And when you see the finished building in a photograph, then you understand how quite complex these sails and geometry are. This is all design of Frank Gehry, an architect from LA in the US. We can talk about the use of the BIM models for construction. And once again, this is the same building I showed you before, the Maple Tree building in Singapore. And we see how in this case it was used for a 4D CAD planning of table forms which were shifted through the bays from the right-hand side to the left-hand side in sequence. And the images show quite clearly the sequence of preparing hollow core slabs, preparing reinforced concrete topping and pouring the topping, and then progressing day by day in 3 zones from right to left. And then, of course, we can talk about BIM being used for operation and maintenance. And this is a model of an airport in Abu Dhabi, which we see both the BIM model on the left-hand side and the maintenance software on the right-hand side showing areas for operation. So, to sum up this first section of my talk, what really is then building information modeling? Well, when adopted well, BIM facilitates more integrated design and construction processes than possible using CAD. And that results in better quality buildings at lower cost and reduced project duration. BIM processes provide a new design and construction capability, and therefore they also change the roles and the relationships among the project teams. We see now that right around the world, BIM has become very widely accepted, and we have new codes of practice, we have new ways of working, new processes, and indeed, the roles and responsibilities of information officers, BIM managers, building BIM execution programs, and other documents are the bread and butter of our work nowadays.
第一部分，什么是 BIM？ 在现在的行业发展背景下 ，BIM 技术已经有了具体的定义和目标。我们需要通过 BIM 技术实现4方面的要求：一、通过 BIM 技术，精确的数字化构建出建筑的一个和多个虚拟模型；二、构建出的数字化模型可以支持设计的所有阶段。相比于人工设计过程，有更好的分析和控制效果。3. 数字化模型为实际建筑和数字化原型，可对其表现和性能进行全面的测试、测量和评估。4. 数字化模型提供用于施工、装配以及采购活动的准确几何形状和数据，从而实现建筑的落成、运维和维护。通过以上4点可以看出，如果在实际工程中运用得好， BIM 比 CAD 更能促进设计和施工过程的整合，从而可以用更低的成本和更短的项目周期，建造出更高质量的建筑。
So, to sum up this first section of my talk, what really is then building information modeling? Well, when adopted well, BIM facilitates more integrated design and construction processes than possible using CAD. And that results in better quality buildings at lower cost and reduced project duration. BIM processes provide a new design and construction capability, and therefore they also change the roles and the relationships among the project teams. We see now that right around the world, BIM has become very widely accepted, and we have new codes of practice, we have new ways of working, new processes, and indeed, the roles and responsibilities of information officers, BIM managers, building BIM execution programs, and other documents are the bread and butter of our work nowadays. So now, let's shift and talk about digital twins. The underlying principle of a digital twin is that I can maintain in a computer a representation of the real physical thing, and by doing so I can stream data into it from the physical thing, in this case a railway locomotive. So I might be monitoring the way the engine is working, the way the train is moving, its location in space, and so on. And at the same time, in the digital twin, I can then ask what-if questions. I can say, what if I increase the oil pressure? Or what if I decrease the lighting? Or what if I maintained this particular part later rather than sooner? And using those simulations, I can make decisions about what is the optimum way to operate that real locomotive. And I can then send instructions directly, digitally, from my computer system to the engine itself, to the locomotive, and act on those decisions by teleoperating it. So the idea that I can use a digital representation to represent the real facility, to do what-if scenarios using it, and then to operate it, and all by virtue of the fact that I have a range of sensors and cameras and other things bringing me information to keep me up to date. That is the concept of the digital twin, and it's that concept that I'm going to describe as we move now and talk about building construction, bridge construction, or any other facility. So in this case, for example, we see on the left-hand side a bridge construction site, and at the top here we talk about monitoring systems. And so we can monitor everything going on in this project, not only physically but also processes going on in the project. We can then build a digital twin of that bridge, both as built and as performed. And then we can use it to do lots of analysis and give instructions to build it going forward. Now, if we want to think about what kind of sensors we can use, well, there is currently a wide range of things that are in use in the construction industry. Things like temperature and humidity sensors, laser scanning, photogrammetry, 360-degree videos and other images, even simple things like barcodes or QR codes, RFID and BLE tags and beacons, equipment black boxes installed on cranes and trucks and other things. Digital reporting by users using their mobile phones or tablet computers. We can use ERP systems for construction companies, and we can even use audio recordings. We can see some of the examples of these. Sensors embedded in concrete to predict what the concrete strength would be to allow me for early stripping. That's already an example of a very simple digital twin. 360-degree cameras mounted on helmets used to take video images, which are then processed using photogrammetry, or laser scanning here on the top right, or handheld tablets used by workers, as in the bottom right here, using the Visilean system to report what's going on. And when we think about applying all of those systems, then we can consider this overall scheme of a digital twin system. The monitoring systems I talked about a moment ago are down here. So we're building the project up here, the physical building twin. We're monitoring it. We're getting raw data. We're taking that data into the digital building twin. We have to interpret and merge that data across all of those different monitoring systems. But if we can do that well, we can get this PSM. What is the PSM? The PSM is the project status model, and that contains information about as-built product and as-performed process. In other words, from a physical perspective and a quality perspective, what have we built? Is it in the right place? Is it of the right quality? As performed process asks the questions, when did we build it? Who built it? With what equipment? And how long did they take? And how long did they spend in that place? Now, given that to begin with, I have the BIM model up here. The BIM model represents as designed product or as planned process. So the BIM models you're all familiar with, the as planned process you can think of as the Gantt charts, production, schedule, so on. If I can compare what's in the BIM model, what I intended to do, or you might call it my project intent information, if I can compare that with my project status model, then I can evaluate conformance, both for the product, are things built correctly, are they in the right place, but also for the process. Were they built at the right time? Did they finish on time? Did they consume the correct resources and materials, and so on? Now, if I can do those things, I can use all of this information and the comparisons to look at what I've done, make value judgments, and I can now then predict performance by analyzing and simulating into the future. Having that knowledge, I can now plan and design more intelligently. That information is stored in the future-looking intent model, because that's now describing what I intend to do in my next production cycle. That then is used to control the function that actually builds the building. So build, control, construction represents the crew, the team, the general contractor people who are now then giving instructions to the site and controlling the building. Of course, I can also have real-time feedback if I have things like safety monitoring equipment and such things to give immediate feedback to the crews and people who are active in the building at the time. And of course, finally, I can accumulate historical digital building twins by taking the information here in the PSM, the project status model, and the information here in the design, the project intent information. By storing both of those, I can contain and maintain a historical digital building twin. That allows me to learn over time and to collect the information that nowadays is mostly lost for the benefit of future construction. And so now I just want to show you just one part of that schema, and that's simulation of the next planning cycle. So imagine now that we are building a building and we are monitoring what's going on, and we want to decide for the next 2 weeks, 3 weeks, a month, should we change our production policy? Should we increase the size of our crews? Should we have more crews, fewer crews? Should we add a tower crane or two? Should we adjust the rate of delivery of materials? Or when do we need information? And so on. And so this system will take user input. The user input represents what we can do, our flexibility in planning. We then run simulations. We simulate alternative plan scenarios. We can optimize them too. And then we can provide a recommendation dashboard to project managers who can then make decisions and feed that back into the digital twin database, which will then be used for the next cycle of construction. What you're seeing here, schematically, is a system that we have designed at the Technion as part of the BIM to Twin research project, where at every point in time, like here, or here, or here, at different intervals, we run simulations from the current position of the project, and we ask the question, if we make such and such changes, where will we be in 2 weeks, or 3 weeks, or 4 weeks' time? And we can do that at the start of every cycle, and based on the spread of risk of where we'll be, we can make decisions and then progress and control the construction. You can see this more clearly here on the right-hand side, where we are comparing two different plans. One plan has this purple outcome, the other plan has this brown outcome, and it's fairly clear that the purple plan brings us further ahead with greater probability and certainty and lower risk than the brown plan, and so we should prefer it. In this slide, we see an animation of how the simulation engine is running for a real project, and this was part of our validation of whether these simulations can be accurate or not. From left to right, in the black line, you see the original plan, construction plan for this project. In the red line, you see the actual that was the project achieved. They, of course, achieved being a little bit late. And when we run the predictions from the beginning, we see that the late completion date was far more likely. It falls in the middle of the probability distribution of all the possible eventualities that could happen. And so that, for the planners, would have been an intelligent thing to do, historically speaking. And more to the point here, we were able to validate that a very detailed and complex simulation of a very large construction project was able to give results that do reflect the actual situation that transpired. Then, information of that kind in a future project might be presented to a user in a dashboard of this kind, where we show different alternate plans over here. The user can select them and then reflect on what each plan might do to the project progress, to the cycle time for individual parts of the building, to the amount of work in progress, and most importantly, to the throughput or the rate of production. Now, all of this raises for us some very interesting questions regarding decision support. In the first instance, DTC, or digital twin construction, is pushing us toward data-driven decision-making. But we can see that this is a move from intuition-driven decision-making to data-augmented decision-making, and then to data-driven decision-making. And that DTC computer systems might evolve from along these different steps. But that raises for us yet another question. Right now, we have systems in production planning and control for construction where humans decide. But clearly we're going towards situations where humans decide, but machines advise us. They give us the information, like in that recommendation dashboard. So the system I've shown you up to now would fall in this category: human decide, machine advise. But perhaps then we might move to a situation where we say, okay, let's let the machine decide. If it can do millions of optimization cycles and I can't, then I'll let the machine decide, but I'll supervise it just to make sure everything's okay. But that may lead us, just as it may in autonomous cars at some point, to a point where we move to autonomous decision-making, or automated decision-making. That's one of the big things that DTC, or digital twin construction, may hold for our future. It also means that a single system might be able to manage many, many projects in a given area, and then it might also be able to optimize delivery of information. All of this raises for us some very interesting questions regarding decision support. In the first instance, DTC, or digital twin construction, is pushing us toward data-driven decision-making. But we can see that this is a move from intuition-driven decision-making to data-augmented decision-making, and then to data-driven decision-making. And that DTC computer systems might evolve from along these different steps. But that raises for us yet another question. Right now, we have systems in production planning and control for construction where humans decide. But clearly we're going towards situations where humans decide, but machines advise us. They give us the information, like in that recommendation dashboard. So the system I've shown you up to now would fall in this category: human decide, machine advise. But perhaps then we might move to a situation where we say, okay, let's let the machine decide. If it can do millions of optimization cycles and I can't, then I'll let the machine decide, but I'll supervise it just to make sure everything's okay. But that may lead us, just as it may in autonomous cars at some point, to a point where we move to autonomous decision-making, or automated decision-making. That's one of the big things that DTC, or digital twin construction, may hold for our future. Now, this is a control room in a construction site in Ireland, and it's run by a company called Mace. Some of the systems you're seeing displayed on the charts are from VisiLean, And this was taken 3 or 4 years ago. Now this is certainly human decide, machine advise. But we can easily imagine that we might get to this, where actually we don't need many of those people in that control room because the algorithms are able to process all that information, look into the future and decide what can be done and make decisions themselves. Now, whether that's desirable or not will remain to be seen, but for now we can certainly say that we're not there yet with the technology, not even close. Because after we monitor things, and we get the data, and we interpret and merge it, we need to get the information. But isolated data is not useful. We need data from multiple sources. So we need to merge and interpret multiple streams of data. And if I look back again at all these different streams of monitoring that we can get today, and we can register them, we can compress them, and so on. So we have acquired monitoring data, and what can we do with it? Well, we have to do data fusion and interpretation. So we have to use all of these sources to be able to decide what is the current object geometry, what are the surface textures, where did the workers go, where did the material flow, what equipment was used and where did it go, what were the information flows, and so on. Because that kind of information is essential to build our project status model. Only then could we compare it with a project intent model, BIM, and then use that for design, plan, and optimize. And as things stand today, we simply do not have that data fusion and interpretation intelligent software.
第二部分，数字孪生建造是通过利用传感器、激光扫描等途径采集到的监测数据，将现场的情况转换到虚拟空间中的映射，在数字映射中也可仿真建筑来指导现场施工。以一个项目为例，我们按照行业规范和标准构建数字建筑主体，对设计阶段、项目计划和预期表现提供反馈，然后构建出 BIM 模型。数字建筑主体和 BIM 动态交互实时反馈，控制实际施工建造，也就有了物理建筑主体。在施工建造过程中，对物理建筑主体采用监测技术，可以提供真实的原始数据，整合反馈到数字建筑主体中，周而复始，从而保证整个过程的信息无损传递，实现全生命周期的仿真模拟。数字孪生技术也可以用于对下一个建设周期的模拟和预估，控制现实其接近项目安排，进而支持后续精确、安全、高效的全生命周期管理和决策。
Data fusion and interpretation intelligent software. But I can say that whoever does develop this stuff, that's where the gold is. That's where the value in the information will accrue, and the companies who are able to break this artificial intelligence barrier will be able to commoditize all the monitoring information and really provide valuable information for digital twin construction. And I think this is the thrust that many research projects are working toward nowadays and should be in the coming year.
第三部分，从 BIM 到数字孪生建造的发展。BIM 是典型的静态信息模型，从数字孪生建造则可以实现动态信息接入。在数字孪生建造的过程中，需要采集多学科、多物理量的监测数流，整合理解后，从而得到一个项目的意向模型 PIM。经过设计、计划、优化之后，得到一个更为真实的项目状态模型 PSM。
I want to just recognize in this digital twin construction area the contribution of my colleagues in the BIM to Twin project. They are a range of universities and companies across Europe. And finally, I want to tell you that these days and at this meeting, is the launch of the new edition of the BIM Handbook in Chinese translation, in the 3rd edition. The BIM Handbook has up to date 3 editions. We're currently working on the 4th edition. And it's gratifying to know that it has been translated into Korean, into Portuguese, into Korean once again in the 2nd edition, into Italian, into Chinese in 2017 in the 1st edition, into Portuguese in the 3rd edition, and now in 2023 into Chinese once again. And so I want to say thank you very much. I hope you have found this interesting, and I am available to answer questions. Thank you very much.
最后，在 BIM 和数字孪生的结合方面，前人总结了很多经验。我们现在有非常多的 BIM 手册可以参考，实现 BIM 技术下的精益建造。